Hello everyone, I'm Young from Rakuten, and today I'm going to introduce our work on learning similarity preserving binary codes for recommender systems. First of all, let me explain our motivation. Binary hashing is a technique that converts floating point continuous values into binary codes. Here, for feature vector x, we need 8 bytes for each value if we use 64-bit floating points, while we need only 1 bit if we use a binary code. Several techniques for binarization have been introduced. For example, we can set a hard threshold like a sine function so that we can convert values smaller than 0 to -1, otherwise +1. Recently, sub-thresholds such as scale tanh function is getting more attention with neural network because it's differentiable and the loss can be backpropagated. Hashing-based recommendation utilizes binary hashing to reduce memory requirement and accelerate the recommendation speed. In our paper, we explore a new hashing-based RS model, Compact Cross-Similarity Recommender, namely CCSR, which is inspired by cross-modal retrieval literature. We demonstrate that maximum posteriori MAP-based similarity loss works well in top K recommendation task. We analyzed recommendation performance with different binarization methods. We show that simple sine function still performs well compared to other more complicated methods. Let's review previous works on hashing-based recommender systems. Previous systems mainly consist of 3 modules: feature extraction module, user item interaction modeling module, and binarization module. Feature extraction module maps input features to latent space. Interaction modeling module learns user item similarity and interactions. Binarization module converts continuous features to binary features. Previous work had different design choices for each module. We summarize them in table 1. From now on, we introduce our model CCSR. For feature extraction, we utilized autoencoders. For user item interaction and similarity modeling, we utilized the dot product. For loss function, we used MAP-based loss. We also added balanced loss to balance the number of +1 and -1 in binary codes. The optimization is performed by minimizing all losses on continuous values. Here is the architecture of CCSR. First, let us look user-side autoencoder. We take user input, for example, user rating on all items. We utilize autoencoders to extract latent features. We set the dimension of size of the latent feature as a hyperparameter and tune it for the best performance. The same architecture is used for items. For items, we can have ratings from all users on target item. We learn better hidden features by optimizing 3 losses: autoencoder-based loss, MAP loss, and balanced loss for better binarization. At the inference time, we convert the learned continuous features to binary codes and utilize Hamming distance to recommend top K items to a query user. From now on, let me explain the experimental setting and results. We utilize 3 datasets: movie less than 1 million, Amazon review, and Ichiba purchase dataset. Here we list number of users, items, and ratings. We compare the CCSR with methods from 3 categories: rule-based methods, such as random and top; matrix factorization-based method, such as CFS, CF CodeRec, or AECF. And we also compared it to cross-retrieval-based method, namely DJSRH. For binarization, we report the result using sine scaled tanh and sine scaled tanh. Note that scaled tanh return continuous values, not +1 or -1, which means it does not return binary code. Here, we compare CCSR to MF-based hashing-based recommender. We report NDCG at 2, jigs at 10, with the code length from 5 to 40. Note that the code length means the dimension of latent features. In moving lens and Ichiba dataset, CCSR performed the best. In Amazon dataset, CCSR performed second best. From the result, we can see that CCSR works better than MF-based hashing recommenders in most cases. To understand when similarity loss works well compared to rating reconstruction loss, we used continuous features without binarization for recommendation in moving lens 1 million dataset. We divide test users into two groups. One group obtained better result in NDCG at 10 with the CCSR continuous, and the second group with the better result with the AECFC. After analyzing their features, such as average ratings, average number of ratings, and standard deviation of the ratings, we found that CCSR is helpful for users who rated less items and with higher rating variances. This is because AECF benefits more from the more ratings as it tried to reconstruct original ratings to learn the representation. With higher rating variance, cross-retrieval-based models learn better representation using similar and dissimilar pairs. Finally, we show the effect of different binarization method. We can see that models performance generally drops when we change ST to SST. Here we visualize the reason for change. Here we have three continuous value features, namely A, B, and C. In ST models, continuous features are close to +1 and -1. Here A is more similar to B than C. But B and C are equally similar to A after converted by SST. Let me conclude my talk. We found the similarity loss performs well on hashing-based top-K recommendation tasks. Even though differentiable scaled tanh is popular in recent discrete feature learning literature, performance drop occurred when scaled tanh output are forced to be binary. CCSR is helpful for users who rated less items and with higher rating variance. Thank you for listening.